In this tutorial, I'm going to show you how to use double integration method to determine the beam displacement. Here we have a beam, pin support, the support A, and roller support and support B, and the C is a free end point. At the point C, we have a concentric load P applied on the point C. And now first of all, we want to determine the reaction force. So at support A is the pin support. We have reaction force in y direction AY and reaction force in x direction AX. And support B, we have reaction force BY. So we can easily determine the reaction force based on the equation of equilibrium. So in x direction, AX only have one force is AX equal to 0. Okay, so in y direction, so we have two unknown force AY and BY. We can write down the moment equation at support A equal to 0. So at support A, we have a moment first of all from BY. So BY times 2A. So it's one moment. The other moment is P. So P is times 3A, leave arm 3A. So these two moments are in different directions. So we put a negative over here equal to 0. So we can derive By equal to 3 over 2P. So this is By. And for Ay, we can derive Ay based on the equation of equilibrium, bending moment equation of equilibrium at point B. So first of all, Ay have bending moment is Ay times 2A, and B and P have a bending moment is P times A. And these two bending moments are in same direction. So it's positive equals 0, then we can derive Ay is equal to negative 1 over 2P. So let's put these two reaction force on the beam. So first of all, Ax equals 0, so we can just don't show that. And Ay is negative. That means our assumption go up is not correct. So the real direction is going downwards. So if we just correct this direction, so we will have so that going downwards. So this is Ay is 1 over 2P, and By is positive 3 over 2P. So we write down here is 3 over 2P. So this is the reaction force. So after we have a reaction force, then we can apply the double integration method. So the double integration method, we using the elastic beam theory. So based on elastic beam theory, we have derived that EI, the second derivative of the deformation curve, times EI is equal to the bending moment. So if we want to know the displacement, first of all, we need to calculate the bending moment. So now we need to do moment analysis on this beam. So if you can draw the bending moment diagram, you can find that the bending moment diagram is like this. So it's two curves. So we cannot use one functions to determine to represent these two curves. So we must have two moment equations. First is for the segment AB, second is for segment BC. So once you have some experience, you can find, because here we have no discontinuity at the point B, so we definitely need to find the two equations for the bending moment. Okay, so first of all, we need to find the bending moment at the AB. So for segment AB, we arbitrarily cut a section over here. So if say this is cut A to A, we need to draw the free body diagram over here. So this is A to A, and this is support A, and we have force 1 over 2P, this point A. And on this cutting section, we have a shear force, we have a bending moment. So here we don't need to consider the shear force, so we only consider the bending moment. And the coordination systems y, x. So from the support A to the cutting section, the distance shown here is x. Okay, so then we can easily write down the equation of equilibrium of section A to A. So bending moment section A to A is equal to 0. So based on the moment equation of equilibrium. And if we want to write down the equation of equilibrium, we need to assume the positive direction for this equation. So if we say the positive direction is go clockwise, so first of all, we have a reaction force 1 over 2p have bending moment, so it's go counterclockwise. So it's 1 over 2p times the lever arm x. And at section A to A, we have bending moment m, so it's also counterclockwise, so it's negative equal to 0. So from this we have m equal to 1 over 2 px. So this is the bending moment for the beam segment AB. Okay, so we can say this is for this curve. So this curve, if we say this is bending moment m1, okay, this is y1. Okay, so because we need to calculate two equations for the bending moment. So this is for AB. And for BC, similarly, we need opportunity cut a section. If we say this section is B to B, and for this cut, we need to draw the free body diagram as well. So this free body diagram is shown here. So we have support A, we have support B, and support AF reaction force 1 over 2p go to downwards, and over support B we have 3 over 2p go upwards. And on this cutting B to B, we have shear force, we have bending moment M. Here we see M2, here is M1. Okay, so similarly we need to draw the free body diagram. We need to draw the coordination systems. So coordination, say this is x, this is y2, just differentiate from the y1. So we have the distance from here is x. So similarly, if we write down the equation of equilibrium at section B to B, the moment equation of equilibrium equal to 0, positive direction go to clockwise, and we have 1 over 2p have bending moment lever arm is x, so it go to counterclockwise, so it's negative. And for the support B, it's go to clockwise, so it's positive 3 over 2p times the lever arm. So the lever arm is here, so this is lever arm, so it's x minus 2a. So this is lever arm x minus 2a. So this is bending moment from the support B, and we have a bending moment m2 on this section is go to clockwise, so counterclockwise, so it's negative m2 equal to 0. So then m2, we can rearrange this equation, then we come out m2 equal to px minus 3pa. Okay, so this is the moment equation. So once we have this bending moment equation, then we apply this elastic beam theory, then we can, based on the double integration, we can find the deflection on any point of this beam. So we will show you this procedure in part 2.